the sheet metal forming or sheet metal bending. In this picture, you can see the punch is coming down and the die is is a V-shaped die. And now when you push the punch down, then if you leave the punch, it will be bent like this. Little bit spring back. It is not exactly the same angle. Little bit spring back is happening. So in order to achieve the required angle, the die angle, so you have to make the V a little bit narrow so that you can achieve the required angle, because there is always a small spring back in the material. And suppose if you want to have uh, up, if you want to punch this hole, then you push this uh, punch here and the shear this area. This area is, you cut it off, you remove this hole, the metal outside this piece. So this is area shear, which is 2 pi r perimeter times the thickness. Suppose this is thickness is backside here. This is my thickness, okay? So this is the area you want to remove. So 2 pi r t. And the force required to cut off this piece from this metal uh, sheet, then you have to use force. Stress, shear stress equals to force, shear force per unit area shear. So I want to find FSH stands for shear force. Okay, shear force. So you can find out shear force equals to shear stress times the area shear. And usually the shear stress can be just estimated. How much is if you know the ultimate tensile strength, you multiply by 70%. That gives you the shear stress of the material. Do you understand this? Okay, let's go to the next. Shearing means cutting off some metal from the sheet metal bending, like this punch is coming down. If you take a closer look, and once it hits this uh, sheet and it removes this blank, we call this as the blanking or punching. Sometimes mm, this blank the is the part, or sometimes is the sheet is the part. This is not a part like a scrap piece, so it means this like a sheet with a hole is our required part. But the formula is this one, okay? Either is shearing, blanking, or punching. These are the same formula. So what is the sheet metal bending? The punch is coming down. This is a specific shape, and you see this is the, if I draw it, if I draw a sketch here, suppose this is the punch radius, okay? This is the punch radius, okay, RP. And then this is the V or certain shape, the die of a certain shape, and you put a metal sheet here. Okay, you bring the metal, you bring your punch down. When you bring your punch down, it squeezes this sheet metal into the shape of the die, and this is the, if you draw a line here, die angle, and this is the punch angle. So if I say, the line has an angle 180-degree, right? So if you draw a line here, you draw a line here. So you will say alpha die is there as well as alpha die is here. So what is the angle of 2 alpha die plus alpha punch equals to 180-degree. This will help you in finding some unknowns later. So this is the equation of a line. Please note it down. And here, from this center till this edge, this is the distance L. And you see, this is the, sorry, let me share with you. This is the width of the sheet metal, okay, into the paper. And this is the thickness. So when width of the sheet metal is very, very large than the thickness, so we can assume it's a plane strain. Von Mises. Let me grab this one. What happens when the punch comes down? Then this metal, suppose if I increase this, yeah, if I zoom in, this is the thickness of the metal. You see, in the middle is a neutral axis, mean the stresses change from the top compression, this the compression here, and over here is tension. Up until here, this is compressed. So sigma with negative. Let me change the color here. So stresses are negative in up until. This is positive. Tensile. It's very compression. Up on this is the neutral line. Okay. We just drew this diagram, the sketch. Now let's find out where the strain in the sheet metal strain. And you remember the strain, if I take the width of the sheet metal, and this is the punch radius, okay, and This is the neutral axis. If I draw, so over here, suppose this is theta, this is OA, this is O prime, A prime. So you remember this is the change in length. So delta L over L is the E tensile. Do you know what is OA? OA is, if this is thickness, this is RP. So can I write down R theta? You know S is equal to R theta. So this is like an S. Okay, this is like an S for this. This is S prime. This is S. Okay. So what is S prime? S prime would be equal to the length from this center of the punch radius, center of curvature. And what will happen? Look, RP plus thickness times theta. You agree with your professor? And if I consider OA, S equal to R theta for OA, what is RP plus T by 2, half of the thickness of the plate times same angle. You see my point? So RP plus T times theta minus RP plus T by 2 times theta divided by RP plus T by 2 times theta. So if you do the math here, let me show you. Let me show you over here the strain analysis, tensile strain analysis here. So theta is cancelled, so RP plus T minus RP minus T half divided by RP plus T by 2. This is cancelled, so T minus T by 2 is T by 2. Agreed? So now I want to write down RP plus T half T1 by. So if I bring this in the denominator below this value, what can I write down? I can write down tensile strain. So 1 over 1 plus punch radius divided by the half of the thickness of the sheet metal. This is the tensile strain from the tensile test. But neutral axis, it shifts about 5% of the compression side. So let me show you. This is the same tensile strain. If you want to actually find out the strain, this would be like this: 0.8 to 1.8 RP over T. Then comes another formula for the true strain. This was the engineering strain. This is engineering strain. And now the true strain, you already know true strain. What is true strain? The instantaneous true strain is represented by epsilon, the change in length, sorry, Ln, final length over initial length. Arc length, this is what R length. So if I say final arc length is RP plus T times theta divided by initial length, RP plus T half times theta. This is the true strain. Okay, this is a true strain. And then you do some simplification. Okay, so I can write down epsilon T equals to Ln and this is equal to, look, this is also equal to, if you remember, the at the true strain at the necking, if this is a tensile stress, I can say this is the reduction in area, RA. So I can write down Ln, 1 mean 100%, 1 minus reduction area, that is equal to Ln. So I want to find out the RP, the punch radius, in terms of RA. If you do the math here, ln is cancelled, because if you take the exponent on both sides, exponent and ln, they are inverse of each other. They will cancel out. So you are left with, if you do the some simplification, you get this answer. 2 times area reduction minus this is your punch radius formula if I give you. So if you see the stress strain curve, you will see we are working in not in the elastic region, but the plastic region. This is elastic region and this is all plastic. So we are working, our strain, suppose E elastic, it should be less than E tensile. What is E elastic? You know, stress equals to E times the strain. This is my yielding point. This is my stress at the, before the yielding, it behaves like a, like a linearly. So when you see such a problem, I will do some check with a E tensile. What is E tensile? 1 over 1 plus 2 RP over T. Whether is this greater than E elastic? If it is greater than, this is a plastic strain. Make sure you are working in the plastic region. And then sometimes there are different material behavior. I want to show you different examples. Okay, suppose if this is purely plastic material, the yielding is happening and is straight, there is no elastic, all the material is plastically deformed. Okay, this is my strain, true strain. So this type of material will have a neutral axis, and the stresses are here. This is my positive side, this is my negative side. Okay, this is the negative side, yielding is happening. This is my positive side, yielding is happening. And this gives our bending moment, our torque. Okay, and how, what is the value of this torque? Let me show you. Let me show you that the bending moment is R times the force, the bending force or the punch force. So the force equals to sigma times area. Sigma area in our case is different over here. This is T half, this is T half. So I can take that one over here, sigma, the area shear is area bending is B times. B is the width of the sheet metal. Agreed? And this is my area, which is bending area. This is my sigma yield. And what is R? R is equal to T half divided by 2, from bending moment happening in the upper half and the lower half. This is T half by 2. And it is happening in two sides. So you have multiplied by 2. Let me show you. So if you do the math here, over here, like, let me write down the bending moment is equal to sigma yield times the width of the sheet metal times T square divided by 4 for perfectly plastic material. Okay, this is the bending moment formula for perfectly plastic material. You don't see any yielding like over here. There is no yielding here. So there are different cases. This for perfectly the bending moment formula for the perfectly plastic. So let me show you the slide by slide explanation here. I don't want to derive all the bending stresses, bending moment, but I want to show you which one do you need for your form problems. This we already did that, so we don't need to cover. You already know about these true strain, engineering strain. Punch radius formula for due to the true strain is this one. One check you can do when you see the problem that the elastic region is smaller, the stress is smaller than the plastic region. So this is the perfectly plastic case. Okay, what is the bending moment for perfectly plastic case? It's is calculated like this. This you can find it out. So let me show you. Now elastic plastic, okay? If a material is little bit ductile and elastically deformed, then plastically deformed. So this is like a sheet metal, okay? This is like a sheet metal thickness, okay? This is my uh, T by 2, agreed? And this is B, okay? This is my B, the width into the paper. Okay, now, so we will perform the same analysis like R cross F. F is stress times area. So this is for the elastic region and this is for the plastic region. So I don't expect you to do the derivation. I'm trying to explain. If you understood one case, you can see the formula is sufficient. Now we have to calculate, add them together, elastic and plastic. So this is for the final bending moment formula for elastic and plastic region. And then comes the third case, strain hardening material. You see, is different. The first one was, you see, strain hardening is straight line, the slope with a slope here. It is the thickness. You see, this is the thickness and this is the width of the sheet metal. And this is the stress. Stress is written by sigma yield plus the Ke. So MB is for this one is this. We already calculated one of them here. Strain hardening, triangular section, strain hardening. The total strain hardening formula is this one. So this is the third case. The first case was the bending moment calculation for the perfectly plastic case. Second case, elastic plastic. Third case is strain hardening. Have you understood these three cases. Now let's go to the sketch. For only 3 cases will be discussed here. That is sufficient for our analysis. Now, when you push the metal downward, when you push it downward, the metal supports are here, and you see it moves upward. When it moves upward, so sorry, with the push, the material goes inside the punch. When it goes down, the friction force is at the contact of the die, at the contact of the die. This is the contact, okay, at the contact of the die. And then friction force is opposite to the motion of the material sheet metal. Okay, you see my point? So F equals to as upward mu times n. You agree with me? And the bending moment is happening here, and the shear force, and this is the force diagram. And then it's not shear force, the bending force. So this is the formula. Please write down this formula in your formula sheet. And the maximum bending force can be calculated by some calculus using some second derivative with respect to the variables such as the die angle. So we can find out what is the maximum bending force and the die angle for the maximum force. So please write down this formula for the finding the die angle. It depends only upon the coefficient of friction. Mu increases, the bending force also increases, and also the die angle also increases. Let me show you the relationship. As the coefficient of friction increases, the die angle also increases, and the bending force also increases. But in actually, what happens? There is another concept of spring back, that the material does not conform exactly to the die angle, but it leaves a little bit some spring back happens. So you see over here, this was a final punch position. It should have gotten a 90-degree, but it springs back. This spring backs can be found with another formula. How do you find out the spring back? Let's do this spring back analysis here. Explanation. Spring back due to the loading, due to unloading. The final punch, final equal to the bent minus elastic. So 1/ρ final. This is our final. After the spring back, this is our actual bend, and this is the elastic recovery. 1 over bend, the radius of curvature, right? Minus 1/ρ elastic. Or yield. So if I say that this is my alpha bend, the punch angle, this is my alpha delta alpha by 2, delta alpha by 2. This is my final. Delta alpha equals to alpha final, sorry, alpha bend. Now I'm going to show you different cases. For fully plastic, what is the spring back or the final or the change in angle, uh, bend angle, spring back for fully plastic. So this is my final. Change in the angle of the sheet can be calculated this formula. And for fully plastic, second case is fully plastic. This is the formula. Similarly, fully plastic. Elastic plastic, the spring back. Is this formula for elastic plastic. The ratio of the actual change in angle divided by the alpha bend. And for strain hardening, is the different formulae. Strain hardening alpha diangle, alpha punch. Yes. I will say you please write down this formula for the strain hardening, the ratio of the angle, change in angle divided by alpha punch. This is the change in angle of the sheet. Delta alpha is the change in angle of the sheet, alpha final minus alpha bend. Alpha bend is the punch angle. With that, we have finished this topic. I'm gonna solve this problem next time.